Hello, this lecture is on line and surface integrals, and it's an introduction to be followed by, say, 8 to 10 lectures on the detail between line and surface integrals. Okay, now each of these comes in two forms, scalar and a vector form. So let's start with line integrals, scalar. And lines can appear in the plane or space, so let's start with a line in space. And a line is really a curve which may or may not be straight. So it's really a curve interval. And it has a starting point, let's call it A, and an ending point, call it B. All right. Now we're going to integrate this line or curve. Integration means to take this thing and chop it up into pieces, and each of those pieces, we'll draw a piece right here, it's a super small element of length, and so we'll call it the differential of arc length, and the symbol is d little s. Now for each one of these d little s's, we're going to multiply times some function. So we need a function, and we're in space here, so it's going to be a function of x, y, and z. So the line integral is to take that function and multiply it by the element of arc length, d little s, and to add them all up over that curve. So here's your scalar line integral notation. So what does this measure? Well, if this function is 1, then we're just integrating over the super small arc lengths, which means we're adding them all up, so we're going to get total length of the curve. Okay. Another application would be if f is some kind of density function, delta. So it measures the mass at each point along the curve, and we integrate, we're going to get total mass. So you can think of this as maybe a rope that's lighter at one end and heavier at the other end. When we compute the line interval, we're going to get the total mass of that rope. Or F could be anything. Depends on the application. Chemistry, you might be measuring something else. All right. So this is a scalar line integral. Now let's talk about a vector line integral. So what we need is to replace this scalar function with a vector function. And let's say the vector function looks like that. So it's a vector field, like electro or magnetic or gravitational. And we're going to multiply the vector field times ds. So we're going to integrate over the same curve, and it's going to be f, vector field, times ds, d little s, arc differential of arc length. But we're going to be measuring things like work, how much work it takes to move, say, a particle from A to B along this curve. How much work is done by the vector field? Say the vector field is gravity, as the example. Well, the multiplication is not a scalar multiplication. We have to take the vector f and dot it with the unit tangent vector. The unit tangent vector. So we need a dot unit tangent. Now this is a measure, when you add them all up, of how much, again, if this was gravity, how much work is done moving a particle. So in this example, we're typically talking about work. Or if this vector field is some kind of velocity field, something, wind blowing or something, then we're measuring not work, but some kind of flow along the curve. Okay, so those are the kinds of applications you can do with line integrals, vector line integrals. All right. Now, if we take this line or curve in space and stretch it, it becomes two-dimensional, and it becomes a surface, and we're going to integrate. So let's draw that. I think we're done with this. So we're back to scalar. We're doing scalar surface integrals in blue, I think. So what does the surface look like? Well, it looks like, I don't know, maybe something like that. A surface. And let's assume this surface is in ambient space, so we still have our XYZ coordinate system. Okay, so here's our surface, big S we'll call it. And instead of an element of arc length, we're going to have an element of surface. So it's a super small element of surface. I'll draw it big so you can see it. And it's going to be a differential of not arc length, but capital S for surface. So for each one of these super small elements of surface, we're going to need a function. So we're going to need some kind of function here, and it's in space. So we have a function here, defined everywhere the surface is defined. All right, and we're going to integrate. What does that mean? It means we take our function and multiply it by the element of surface area over, not the curve now, but the entire surface. Okay, so again, if f is 1, if this function is 1, we're just taking these little ds's and adding them all up throughout the entire surface, so that gives us surface area. Okay. And to be consistent with the last example for line integrals, if f was some kind of density function, and we add them all up, we're going to get total mass of that surface. And f could be anything, depending on, again, the application. Okay, so that's scalar surface integrals. And let me just emphasize, we haven't talked about how to do these calculations yet. That's the next, 8 to 10 lectures. All right, scalar surface area. We now do vector surface integrals. Okay, so how does that work? Well, we need a vector. So we replace the scalar function, okay, with some kind of vector field, just like in line integrals. Maybe it's electrical or something. And we need to multiply it. Okay, so we need to take the vector field and multiply it by that element of area, ds, d big S, compute the surface integral over the surface. So it's just like this so far, except we're replacing scalar with vector. But typically what we're trying to calculate here, say this is an electrical field, is the flow or the flux of electrical charge through the surface. So that calculation includes multiplying f with some vector associated with flow. Well, that vector, I think you can see, is going to be the normal vector, the unit normal vector. So we get this dot this to get flux. So it's F dot unit normal times the element of surface. So again, we don't know how to do this yet, but we will soon. So this is called flux. And in electrical terms, if we're in electrical field, flux would be just the flow or current, electrical current. All right. Now, there's a whole bunch of formula associated with how to do all of these things. So, not necessarily red. Well, actually, it's usually vector fields. So we have all these formula for flux for surfaces and flux for lines and work for lines. I have all these formula, and for each one of these, there's a kind of a formula that works for all the cases. So we'll be studying all of this over the next several lectures. And I want to point out that associated with all of this are the four fundamental theorems of multivariable calculus: gradient, Green, Stokes, and divergence. And those four fundamental theorems are the basis of what we call Maxwell's equations. And Maxwell's equations are really important to all of science, be it physics, engineering, the study of the planets, how they move, rocket science, chemistry. So I guess my point is, this topic is really, really important. Thank you. End of lecture.